Well, thank you for that good introduction. I appreciate it. And I have to tell you, I'm really excited about being here because what you're going to hear today is a story. This is not a technical deep dive. If you want a technical deep dive, time to leave. But it's a story that I've just put my heart and soul into for the last 9 years, and it's just so satisfying to be able to tell this story right now. So, we'll get going. So, you're going to hear about how the Vulkan SDK was created. You're going to get some basics about the Vulkan API and the Vulkan developer tools. And I'm also going to tell you the story about how the present-day LunarG was created. So there is some important context that I have to start out with, like who is LunarG, who is Kronos, what is Vulkan, and why Vulkan. So bear with me, but I feel like this context is needed. Then I will tell you about the existential events that occurred 9 years ago, right before the launch of the Vulkan API, and it did contribute to the rocky beginning of the Vulkan SDK. I'm going to give you some very brief overview of the Vulkan SDK and some of the Vulkan developer tools. Not all of them. And then that additional information will give you appreciation for the mad scramble, the benefactor, and stabilization. And I'm going to finish then by talking about some of the technology challenges that we had to overcome in the beginning and we're still dealing with today, or should I say opportunities, because we've been able to find solutions to these challenges. All right, first of all, who is LunarG? So we're independent, we're privately owned, we're a software consultancy, we're a bunch of software engineers that are passionate about 3D graphics. I have a staff of industry-leading experts with decades of experience in multiple graphics APIs and GPU technology. We develop proprietary and open source tools, drivers, performance tuning, developer tools. Originally, it was founded in 2009, and it's headquartered in Fort Collins, Colorado. So that's 1 hour north of here. So this is home for me. I've lived in Colorado all my life. And we are the ones that, as Johanna said, we deliver the Vulkan SDK. All right, so I'm going to give a brief overview here, and some of this I can fly through. How many people here are familiar with Vulkan? Raise your hand. Okay. How many people here have actually done development to the Vulkan API? Okay, fewer, but everybody's pretty much familiar with Vulkan. That's good. So very brief overview, cross-platform, cross-vendor graphics and compute API, PCs, consoles, mobile phones, and it's created by the Kronos group. The specification is. That's a member-driven consortium with members from GPU vendors, platform vendors, SoC vendors, tool developers, and game engine developers as well. So lots of IHVs and also ISVs. And in essence, the Vulkan API considers the specification as defining a GPU, is how I look at it. So let me give a really brief history. And it's interesting because 10 years this summer was when Kronos called for participation at SIGGRAPH in Vancouver, in participation for GL Next, it was called, back at that time. And at that time, OpenGL was about 22 years old. Both OpenGL and Direct3D were mature. They were receiving minor feature updates periodically. And there was a general consensus within the industry that the abstractions that were being presented by these graphics APIs needed to be scraped away or removed, more control given to the applications themselves. And hence, sense of this common need to remove this abstraction the Vulkan API started being defined by the Kronos group. So shortly after that announcement, a proof of concept implementation was going on. This was in collaboration between LunarG and Valve. So LunarG wrote the first informal Vulkan driver, Linux, to Intel HD graphics, called the ILO driver. We were trying to figure out last week why it was called the ILO driver. We couldn't remember why. And Valve was porting their engine, their Source 2 engine, to Vulkan as well. There was some validation layer work, very early phases of it going on. And all this work provided valuable feedback to the Vulkan working group within Kronos as well for the 1.0 specification. And then GDC, March of 2015, Kronos announced availability of technical previews of the API, and there were some demos given to key industry players of the Valve Source 2 engine with that ILO driver. And then the API launched February 2016. Okay, so why Vulkan? These will go really fast. It's cross-platform. So the same API you can use for mobile, desktop, and Apple platforms with MoltenVK, the layer translation from Vulkan to Metal. And it has improved cross-vendor compatibility. And this is actually due in large part to one single validation layer for all the air checking of correct usage of the API. Air checking was removed from the drivers in Vulkan intentionally. Once you have all the errors out of your application, why do you need to waste time continually air checking? You get improved performance because explicit control is given back to the application over how they want their GPU and CPU workloads to be executed. It's multi-threading friendly, and again, no more air checking in the drivers. Applications turn on the validation layer during development, do all their air checking. Once they're air-free, they turn it off and they run at full speed. You have shader language flexibility with the standardized intermediate language SPIR-V, which is the official language for Vulkan. This eliminates front-end compilers from drivers, which really reduces driver complexity, and it gives front-end language flexibility that helps improve portability for application developers. And this one's really important. It's an open standard, resulting in a strengthened ecosystem focus. The specification, the conformance test suite, all the developers' tools, they're all in open source. This results in more rigor in the conformance test suite. Everybody can see it. They can find bugs. They can submit bugs. They can submit pull requests to fix the bugs. More controls put in the developers' hands. Something's not working. Is it their application? Is it a driver bug? Now they have the capability to debug down into the tools and find the source of the problem. So it's no more submitting a bug to a hardware vendor and hoping you'll get a resolution. You can debug down yourself and find out where the problems are, and many times work around them yourselves, submit fixes, move on. Vulkan is a layered architecture. So the Vulkan loader is a library that finds and loads the drivers and layers. And then a layer uses a plug-in interface to the Vulkan API that can intercept any of the Vulkan API calls being made by the application. And this is key in enabling, it's a mechanism that enables valuable cross-vendor debugging tools. This picture kind of demonstrates visually what Vulkan did. The driver for Vulkan is very thin, and a lot of what used to be, for example, in the OpenGL driver, is now under control of the application. Now, yes, this does add some more logic and complication to the application, but it also gives them more control and control their destiny and how they're going to use the GPU and the CPU. And then you can see that layers load in between the application and the driver, and this is, for example, where the Vulkan validation layer plugs in. All right, so after that brief history of Vulkan and its benefits, I'll give you a brief history of LunarG, what I call the existential events. So it was Labor Day weekend, 2015. I was up in the mountains, four-wheel driving, camping with my son, off the grid, so they say. And as soon as I got back on the grid, my cell phone started buzzing. It was Alan Ward contacting me. Now, Alan Ward was the previous owner and founder of LunarG. And we went back for many years at HP. He had worked for me at Hewlett-Packard, and that's how we knew each other. But I hadn't heard from him for several years since he had left HP. So I knew something was up, and he was asking me to meet him for coffee. So the next day, I go to coffee, and I will never forget that meeting. The first thing he said to me is, "Karen, do you want to coast to retirement, or do you want to go out with a bang?" I thought the bang sounded pretty interesting. So I started at LunarG October 12th, 2015. But then 3 months before the launch of the API, we had a little bit of turmoil. A transaction occurred between Google and LunarG. Half of LunarG went over to Google to focus on mobile for Vulkan. And the remainder stayed at LunarG with a focus on desktop for Vulkan. Well, this is all fine and dandy, and it also made sense because it was August 2015, if I recall correctly, that Google had announced that the low-level standard graphics API for Android would be Vulkan. Well, back in August of 2015, there wasn't a whole lot of Vulkan expertise available out in the industry. And it just so happened LunarG had a bunch of engineers that knew Vulkan. So it made sense, the transaction. Google needed to beef up some of their resources. The only problem is my engineering team just got cut in half, and the launch is 3 months away. So let me tell you a little bit about some of the developer tools, and I'll go back a little bit more about what occurred at that time. But knowing more about these developer tools, it will help you understand the daunting task that we had in front of us 3 months before the launch. So the Vulkan specification, absolutely necessary, but it's not sufficient for the success of the Vulkan API. Application developers need debugging tools to help them with their application development. So there are a lot of developer tools available in the ecosystem today. What I'm showing you here are the ones that are included in the Vulkan SDK. And by no means is this list exhaustive. For example, RenderDoc, everybody uses RenderDoc. We don't bundle it in the SDK because it has its own very healthy delivery mechanism. So I'm not saying this is an exhaustive list, but again, these are the ones that are in the Vulkan SDK. It is supported on 3 platforms today, Windows, Linux, and Mac. So I mentioned the loader before. This loader is used by all on all desktop platforms, and it provides a consistent method of finding Vulkan drivers. It allows multiple Vulkan drivers to exist without interference, and it provides a plug-in mechanism to enable the Vulkan layers. And having a single loader used by all applications results in a consistent runtime behavior across platforms. Again, the Vulkan validation layer. This is the most valuable and most critical debugging layer today. Everybody that develops a Vulkan uses this layer. And again, it's validating correct Vulkan API usage because drivers don't do it anymore. And once the application is error-free, you turn off the layer and you run at full speed. One implementation of the API usage used by all results in more consistency across vendors. I do know that in the OpenGL days, you had to tune your application either for NVIDIA or tune it another way for AMD. This helps remove that. I'll bring up MoltenVK because it's interesting. In 2018, it became an open source project. So this is a couple years after the launch of the Vulkan API. It's a library that comes from the Brenwell workshop, Bell Hollings, and it translates Vulkan calls to the underlying Metal calls on macOS, iOS, tvOS. And when it became open source, this prompted the creation of the Mac version of the SDK. It was now enabling Vulkan on Apple platforms. And Graphics Reconstruct. It's an API capture and replay tool. It's cross-platform, supported across Windows, Linux, Android, and Mac. And it allows you to capture workloads, the API calls, in binary format for replay at a later time. And it has multiple use cases. We know IHV vendors use it to run Vulkan workloads during their GPU development. We know ISVs use it to get a capture of a bug they have and either submit that to an IHV if it's a driver bug or to debug within their application. What did I do wrong? It's used for regression testing. We use it extensively for regression testing inside of LunarG because you can capture real application workloads to use those as a basis for a bunch of testing. And it's also becoming an underlying engine for many debug tools that are under development today. And new, this released just last week, we just released the crash diagnostic layer. So hung GPUs, crashed GPUs, device lost. We hear over and over again, these are the hardest situations to debug. The crash diagnostic layer is beginning to help with that by using some extensions defined in the Vulkan working group to insert breadcrumbs, I'll call it, and also to get dump files as a result of their crashes. Very strong user demand from this, from the ecosystem. All right, so all those things put together, we bundle them, and that's the Vulkan SDK. Might be trivial, but we have to do it for multiple platforms. We do have to package it. What are the benefits of this? The SDK comes from about 27 total open source repositories. Now you guys are all really smart, I know. You could go build each and every one of those if you want. Better make sure you have the compatible versions. All of them have inconsistent build methods. And then install the build artifacts on the system to get ready to do your development. But with the SDK, we're doing this for you. We do a lot of curation, working with the repository owners to make sure we have good commits, that we're getting compatible versions integrated together. We'll do the system installation. We have a Vulkan configurator built and ready to go. And it also has a license registry. So by binary, we will show the licenses and copyrights that are contributed to that binary from the source. And this is important for corporations, that they need to scrutinize the licenses that are being used within their organizations. And new last week, we had a big release last week. We now are supporting Windows on ARM. That's our newest platform. And the reason for this is that we were getting quite a few requests from it. The demand for it was increasing. What we see in the industry, this platform seems to be increasing on market share quite quickly. I think this architecture will go quickly. The performance of these systems is very zippy. We have a few inside LunarG. We've been very impressed at how they perform. So we anticipate that people will want to create native ARM games or applications for these platforms. And the workflow for developing on Windows ARM is identical as it is on developing in Windows x86, x64. So the Vulkan SDK here, the darker blue boxes, these are all things that LunarG has created and continues to enhance and maintain. The lighter blue boxes are things that we contribute to, but others in the ecosystem are the primary curators of those repositories. And then the gray boxes are things we don't really contribute today, but this just shows you that we are pulling in tools from the ecosystem that others are responsible for creation and maintaining. You can get the SDK from the SDK download page. And this is the first time I can show this picture with a box around the Windows on ARM tab there for getting your SDK for Windows on ARM. We have also Linux, Ubuntu packages, and a tarball, we call it, and SDK for Mac. Download rates are very healthy. Just Windows alone, we're running around 38,000 downloads per week. Okay, that gives you a little bit of appreciation of some of the stuff that's in the SDK and the developers' tools. Let's talk about the mad scramble that was occurring 3 months before the launch of the Vulkan API. So you remember, I lost half my engineering staff. Well, the API launch was 3 months away. We had to get a validation layer, a loader, into an SDK. We had to figure out how to package an SDK. What packaging technology will we use? How are we going to deliver this? Oh, yeah, by the way, I had to create a mechanism for launching and delivering this SDK for download. There was a lot going on. It was a pretty crazy time. I love this picture. So, this picture was generated very recently. One of the engineers on our staff, Artem, he does the synchronization validation work currently. He asked ChatGPT to give him a picture of the Vulkan dragon dealing with the synchronization API. And this is what he got. But quite honestly, that picture represents how many of us were feeling inside LunarG 3 months before the launch. And so, yeah, we like this picture. It's becoming quite famous inside LunarG. Actually, I will have to tell you that the engineers knew what they were doing. Although we were down half in staff, the ones remaining had been there for the last several years. They knew what they were doing, but they also knew the challenge that was in front of them, because they knew. At any rate, we had a coordinated launch with Kronos, the 1.0 API specification, and the first Vulkan SDK, both launched February 16th. There was so much pent-up demand for this API that both Kronos servers serving the specification and my server serving up the SDK crashed from just too much demand, too many requests. Fortunately, both of us were able to get our servers back up quickly and service all the demands. But it was the most exhilarating day for me that the launch was a success. It was really a proud moment that we were able to achieve it. All right, so the Vulkan SDK, it's free. It does not generate any revenue. It comes from all open source tools. So how is this work funded? Valve was the initial sponsor and benefactor of the Vulkan ecosystem and still remains steady and most generous supporter of LunarG to this day. They fund ecosystem development regardless if it benefits them directly. If they see a benefit for others in the ecosystem, they are funding it to make this happen. This is why I call them the benefactor. And they were very strategic in their intentions and their thinking. They started this funding before the launch of the API. They knew that developer tools were an absolute must for the success of this API, and they wanted it to succeed. Kronos did not have the means to staff and run the projects that were needed to be able to deliver this SDK and all the developer tools in it. And hence why Valve, I call them the benefactor, has been funding since a couple years before the launch of the API. Google provides significant contributions to the ecosystem through their own development of highly valuable tools, such as Angle, their GLES to Vulkan layer, and they also provide much of the curation and support for the shader compiler toolchain for Vulkan as well. And they're also providing some financial support to LunarG. We do quite a bit of work on developer tools per their interests and priorities for their business. And then we also get some support from Samsung, Qualcomm, ARM, AMD, and Meta. All these people are providing some level of support to us to work on different aspects of the developers' tools. So why did we succeed in the beginning? 3 months to launch, a new CEO and engineering director, half the engineering team. Well, there's nothing more motivating than knowing what you're working on matters, and it will have a positive and broad impact in the industry. That was extremely motivating for the engineers. And yeah, we were a ragtag team in the beginning, but that purpose is what got us pulled together, focused on what we had to do to get that first SDK out. And again, I cannot overestimate or overemphasize how generous Valve has been as the benefactor of the Vulkan ecosystem. Here I was, an organization that just lost half its engineers, and they could have walked. They stayed behind it, knew that we would build back up and get back to where we were before. And without their support, the SDK would not have launched with the Vulkan API in February. So we've stabilized. There's strong Vulkan API adoption is the low-level standard. And more companies are actively participating in building the ecosystem, and this is enabling benefits for everybody. And LunarG, we listen to the Vulkan application developers. About a year and a half after the first SDK, I started doing ecosystem surveys every year, determining what are the gaps, what are things that are going well, what do you want more of, what do you want less of, what are your challenges as a Vulkan application developer. And we listen to these surveys and study them closely. It will guide the priorities of what we work on in the next year in terms of enhancements, such as the crash diagnostic layer. That has been a very highly requested item from the ecosystem. The other thing that has occurred is that in the early days, it was hard for me to find the right software engineering expertise that could come on board quickly and really deliver value inside LunarG. That's not the case anymore. What happens when I have openings is that there's a lot of interest of people out there in the ecosystem who want to be part of this mission of building these developer tools. And I get extremely talented candidates. Sometimes it's hard to decide between multiple candidates, but it naturally attracts the right people for the job. And the team that we have built up at LunarG, I'm extremely proud of them and amazed at their competency at what they do. And of course, the LunarG purpose does continue. Now, I have to tell you, I joined LunarG 3 months before the launch of the API. This is a confession. I had been out of the graphics industry for 18 years, the last 18 years of my career. When I left the graphics industry, I was doing HP workstation work. It was a fixed function pipeline. And I came into LunarG. The first thing I do is I sit down with all the engineers and I talk to them about what do you do, what are your challenges, what keeps you up at night, what makes you excited. And I sat down with one of the lead shader compiler engineers we had and I said, what the heck do you do anyhow? I mean, that's what I was dealing with. But I will have to tell you that it was a blessing for the engineers that I was somewhat clueless about the challenge in front of us. They knew the challenge, but they also knew what they were doing, and they could go do good stuff to get the SDK built, to get the validation layer ready, and they didn't have to worry about managing a panicking engineering director, because I didn't know any better. I'd only been there 3 months. So it was a blessing. So the first Vulkan SDK was quite incomplete. The validation layer was very limited in its implementation, but it was actually pretty good. If you think about it, the API just launched. People are just starting to write applications. And they got some pretty decent validation out of it in the beginning, but it had huge gaps in it, and it was a Windows and Linux SDK only. In 2018, this is 2 years after the launch, the code base was about 90,000. I couldn't find it before 2018, just to let you know. Code base of the validation layer was about 90,000. Today we're at about 730,000. What drives the size of that code base? Valid usage IDs. So each valid usage ID is assigned to an element of the API. How do you use it? And this is what the validation layer is validating at runtime. Now, back in 2017, we were around 2,500 VUIDs. Today, we're over 19,000. Okay, so this is what is partially contributing to the size of the code base of the validation layers. The yellow line shows the valid usage IDs as they're defined by the Vulkan Working Group and released. The green line are ones that are actually validated by the validation layer today. And the blue line, we haven't gotten to them yet. And what we want is the gap between that green line and blue line to get wider and wider. It's going the right direction. So today the validation layer, it's pretty healthy open source project, has pretty robust functionality. In the very early version of the Vulkan API, you were required to bind buffers, textures before sending them to the GPU. Then the bindless attribute of the Vulkan API released, I think, some around 2017, if I remember correctly. This required us to add to the validation layer what we call GPU-assisted validation, or GPU-AV. This is stuff that cannot be validated until it's executing on the GPU due to the bindless nature of the API. The first launch of the validation layers had no synchronization validation. The Vulkan synchronization API was totally invalidated. We didn't release the first version of it until 2019, and that only detected hazards within a single buffer. Then in 2022, hazard detection within and between queue submissions and across queues was added. Let me tell you, the very first one, you think pretty simple, hazard detection within a single buffer. That was 18 man-months of effort. This stuff is hard to validate. Another 24 engineering months to do the release for 2022. And these are smart engineers that are working on this. It's not because we're incompetent. Okay, so we have a CI test farm inside LunarG, and we can do much of the testing of the validation layer, for example, using in software in the cloud, using the mock ICD. However, since more and more validation is moving into the GPU because of the bindless nature of the API, we have to have GPUs in our test center. And GPUs cause issues. Managing a GPU hardware test farm is not trivial. You get hung, locked up GPUs. You need to be able to detect that and recover from it appropriately. But without those GPUs, we cannot test the validation layer code base fully. And we have to test across multiple operating systems. Each operating system has its own behaviors as well, and across multiple GPUs and also Android. So this adds for quite a complicated test center that we need to manage. People might say, well, why don't you just do a software reference implementation for Vulkan and just test everything in the cloud? Well, to keep a software implementation up to date would be a huge task in itself. And I don't think anybody intends to release their applications to run on software-only implementations. We need to be testing real customer environments. So we need this GPU hardware test farm that we have. So the validation layer, we've made a lot of progress, but I'll tell you, we ain't done yet because that API just continues to evolve. So now I'm going to talk a little bit about some of the technology challenges that we dealt with in the past and in the future. We'll find our ways through them. So I've talked about synchronization many times. Very complicated API to validate. And the amount of state tracking that has to go on to detect hazards and the usage of the Vulkan, the synchronization API, it's a lot of overhead. And so we always have an ongoing opportunity to improve the performance there. Many challenges there. And I should tell you, by the way, synchronization validation is optional. You have to explicitly turn it on due to the performance of it. Okay? Objects, Vulkan objects, so many Vulkan objects. The sheer number of them causes complexity in the validation layer. And objects, they all have different functions and usages and rules about when they can be created and how they can be used. That adds quite a bit of complexity to the validation layer. This was an interesting problem we had. So in the bindless functionality of the Vulkan API, resources are accessed by shaders via objects called descriptors, which are grouped into descriptor sets. And only descriptors that are actually used by a shader invocation on the GPU are required to be valid. So a shader invocation might only use 10 descriptors out of millions that they could have had defined. We had an application, I won't name it, I bet many of you might be able to guess it, that without validation running would run at 100 plus frames per second. This application really took advantage of the descriptor indexing. When validation was turned on, it went from 100 plus frames per second to a fractional value. Well, the problem was we were validating all the descriptors, even if they weren't used. So how could we know that they were used? We started using our GPU-assisted validation. We'd instrument the shaders on the GPU to detect which descriptors are actually used, and then only validate those. So there had to be a passback from the GPU. Use this one to the validation. Okay, now we'll go validate that one. Got some very significant performance improvements from it. That project was a very interesting project, but it took about a year to complete it. I talk about GPU AV, but we have performance issues with the GPU-assisted validation. We have to instrument shaders that will be executed on the GPU to do that validation. This can result in bloating of these shaders, and it can hurt performance. Pipeline compile times, runtime shader execution. This is currently top priority by one of my top engineers inside LunarG to investigate this problem and find a way that we can improve the performance, because we have to be able to instrument shaders and do validation on the GPU due to the bindless nature of the Vulkan API. Latency and error reporting. Oh, people complain with each ecosystem survey. It is so hard to figure out. I'm getting these errors from the validation layer, and I can't figure out what I did. Well, half the problem is what they did was 10,000 calls before, because the errors won't get spit out until that queue submit. So the challenge that we have is what is the information we need to keep track of, and how can we do that in a way to not be too slow on the validation layer, so at the time of the error, the user can get enough information to figure out, oh, it was that call way back there that's causing this issue. All right, let me talk a little bit about graphics reconstruct. Remember, this is the application that does API capture and replay. And by the way, my technical lead and architect is sitting back there in the corner. If you have any technical questions about this, I'm pointing you that way. One of the challenges we had with graphics reconstruct, well, so in Vulkan, there's, images can be returned in different order from run to run, regardless of the swap chain modes that you have. In fact, no swap chain mode, presentation mode will guarantee the return order. So this resulted in, we'd have a capture, and when you replay it, you'd have blank screens or flickering or weird stuff going on. And so we had to create a virtual swap chain to solve this problem. I shouldn't say problem, solve this behavior of the Vulkan API that would result in the same number of images in replay as there were in capture in the same order. API explicitness. So Vulkan is a very low-level API, and it's very explicit. And this means that a capture that you do on one GPU will not run on another GPU. In fact, it's not uncommon that even a driver update on the same GPU can result in a capture not being able to replay correctly. But we have use cases. We have some users that they say, yes, we have to have every explicit Vulkan API call stored in that capture file. We need it for analysis. Oh, but by the way, I would like those captures to be able to be played on a new GPU we're in the process of developing. So there's a little bit of a conflict there. We're investigating methods to do this via translation layers or metadata that can be stored, but we do not want to get rid of the explicit API calls that were originally made. the GPU-centric universe. So GPUs, they're no longer graphics processor units. They're very specialized hardware, very efficient, processing large blocks of data with a lot of parallelism. And hence, they're being used for compute. How many presentations did I see that you guys were using the GPUs for compute? Artificial intelligence, machine learning, etc. More and more, less graphics API usage is actually occurring on the CPU, but rendering complexity is still increasing via GPU-driven rendering. And workloads are moving to the GPU because they want to maximize utilization of those performance benefits of the GPU features, and they need to reduce CPU interaction. So work graphs, I think everybody knows what they are. This is a fine example of a GPU-centric universe. Work graphs are giving more autonomy to the GPU. The GPU can feed itself and create more workloads and keep executing. It removes round trips to the CPU. Now, this is currently not available in Vulkan, but this is a prime example of a GPU-centric universe feature. So I can imagine what it will be like for graphics reconstruct with things like work graphs, and we're having some situations like this today. Information that used to be known at a function device call from the CPU doesn't occur anymore because it's happening dynamically on the GPU. So addresses, for example, get baked into capture content. We need to have those addresses changed or translated at time for replay. How do we do that? So think about the challenges or implications for developer tools in a GPU-centric universe. Debugging on a CPU versus a GPU. The CPU, you have your instruction set architecture and you can step through the code. GPUs can be a black box, and they're just intrinsically different. Could you imagine stepping through one of a million items in a massive parallelism environment? So the cross-GPU open source tools that we have today, they're very useful, but they will need to evolve for this GPU-centric universe. And this evolution will need to come from a cooperation between the specification designers, the IHVs, and the tool developers. Or we could go back to the mode where every IHV does their own air checking again. I don't think that would be a good solution. An example of something that can happen at the API level to help developer tools. In Vulkan, there's this thing called buffer device address capture replay. So you enable it in the driver during capture, and when memory is being allocated, you can query the memory location and then use that same location during replay. The current limitation is it's not supported by all vendors. So from the launch of Vulkan to today, there's, in essence, one industry standard Vulkan desktop SDK. I never knew it would become that, but I'm pleased that it has. There's very wide adoption of it. There's strong satisfaction from the ecosystem surveys. It's open and it's free for all developers, and it's cross-platform. And the tools are valuable. They are robust in features and reliability, and they are providing real value to the Vulkan application developers. And of course, the LunarG purpose will continue because we are driven to figure out how to evolve these tools for this GPU-centric universe. So my personal reflection on this LunarG journey, what I have learned is the power of being purpose-driven is really powerful, and it really helped LunarG to overcome adverse conditions in the early days, and actually for many years, because we're not a company with hundreds of employees. We have to be very smart and very prioritized about what we work on, and we have some very difficult challenges. And you know what, doing open source, everybody sees your code, right? So we can't hire people that are afraid other people to see their code. But this purpose has given the engineering team a lot of motivation to do what is needed to succeed. And it attracts extremely talented people to the company. The thing that is most satisfying for me, I'm obviously not a spring chicken. However, I'll tell you, I love what I'm doing. And retirement is not in my vocabulary. I don't even know what that word means. That said, the professional efforts of what I've been able to do and what the LunarG engineering team has been able to do, in my opinion, has given a very useful and impactful gift to the ecosystem. And it's not a one-time thing. It's lasting and can be carried forward as the Vulkan API evolves. So that's my story. How we started out from a rocky beginning as a ragtag team to the set of tools that we have today, and a highly collaborative, energized team at LunarG that I'm extremely proud of, and the state of the Vulkan SDK today. Questions?
Thank you so much, Karen, for this presentation. Any questions for Karen?
Very nice presentation. Who came with this name, LunarG, and what does it mean?
Where did the name LunarG come from? Alan Ward likes moons and celestial stuff. He wanted to name the company Lunar Graphics, but it was already taken. That's all it is. And it makes for a nice logo and pictures you can put on your slide sets, etc. So we kept it.
Any more questions? I have one.
Yes.
Let's say someone comes up with a wonderful tool for debugging or whatever and wants that to be included in the SDK. Is there a way, like, can you apply? Can you say, I'd like this to be included?
Yeah. So in essence, what is my decision process around what we will include in the SDK? So first of all, it has to be pretty clear that the usefulness of the tool is wide. A lot of people, it provides benefit for many use cases for a lot of people. Number two, there has to be someone on the other end of the phone. Someone has got to be curating that tool. When we're putting stuff in the SDK, that doesn't mean we develop all that ourselves, and we provide technical support for all of it ourselves. It's not humanly possible. So there needs to be someone signed up, they're curating that open source project, they're there to take defects if defects are found. So I do a little bit of poking around to see how well supported do I think that is. And that's really what drives it. And then, of course, a lot of the ecosystem survey, a lot of comments in there tell me very clearly where their gaps are and the types of tools they would like to see. But we also think of tools ourselves that they may not know to ask of. Like a very common sense one is the Vulkan configurator. Now, people were complaining about, it's really confusing and hard to find my layers on the system and figure out how to configure them, and I could do it with environment variables, I can do it via the API layer settings, and there's all these different ways to do it. And it was like, gee, why don't we just create a GUI called Vulkan Configurator that will discover all these layers, show you all the options that you can set, configure them, you can configure the layers to a certain environment you like and save it for use at a later time. Very simple concept. They didn't ask for it explicitly. So it's not, do they ask for it, but also we're looking at the comments coming in from the ecosystem, understanding their pain points and designing ways to help with their pain points. So?
Great presentation. What are your thoughts on how would you increase the adoption of Vulkan for Windows games?
You're asking me what is my thought about the adoption of Vulkan for
what
the
would it
industry?
take to raise the adoption there?
To raise the adoption rate? Probably even more simplification of the developer experience. I think that would be a huge contributor to it. personally don't. I know that Vulkan does not move as fast as perhaps Direct3D 12 in some features, but I don't think that really matters because I don't think all application developers want to jump on the latest stuff immediately. No, you know, if it eventually gets there. But those would be my takes. But you know, that question also might be a good question for Tom Olson to answer, the Vulkan Working Group chair. We have him here.
First, I have to credit Karen for the developer survey that she runs. And one thing that may not be obvious to you is how much contact LunarG has with developers all over the world. And they use that and they bring that back to the development working group. To your specific question, we asked developers all that. Use the mic. Sorry. To your specific question, then, we ask developers that all the time because we're fascinated by it. And the answer is real simple. It has to provide a substantial differentiating performance win over D3D12 that we can't get any other way, or it has to have a feature that D3D12 doesn't have and isn't going to. Both of those are nearly impossible to provide. We can be as good as D3D12, but you know, they're both descended from Mantle. They're both similar philosophy, design philosophy. Very hard for us to have more than a 5 or 10% performance difference. And that's not enough to motivate somebody to tear up their D3D12 implementation and replace it. So that's the short answer.
However, there is a benefit of it being cross-platform.
There is.
They can write their application once and hit many platform environments. Other questions? Andrew has one.
Thank you. Sort of a follow-on from that. Now that there is Windows on ARM, so DirectX was originally very much targeted at the immediate mode renderers, desktop-style cards. Vulkan, from the beginning, was designed to cope with tilers and other kinds of architectures. Are you expecting to see more interesting interactions on Windows on ARM now, and with Windows applications now, as a consequence of having ARM available?
I think you're asking, because of Windows on ARM, are there going to be developers that are asking for Vulkan features that are not as prominent right now for the Windows environment?
Are you expecting to see features that are there in Vulkan that aren't there in DirectX, or weren't so native in DirectX?
I'll be honest, I haven't thought about it. I thought more about, let's get Windows on ARM SDK out.
Okay, thank you.
Yeah. And by the way, the SDK was built so that all of the layers are built with the option so that if you had a program running that was x86, it uses the emulation mode feature, or if you have native, then it will get native ARM. So it took some science to get everything in the SDK to build that way. But to answer your question, I haven't thought about it yet. We'll think about that. Other questions?
Well, in that case, there's a question.
It's more than a question. I would like to hear about yourself. What do you think about? We teach computer graphics. I mean, I'm a professor in computer graphics, and it's always this dilemma of teaching computer graphics with Vulkan or using something else. And a couple of times I've tried to use Vulkan. I mean, I have not been successful because it kind of, the learning curve is kind of...
Vulkan is not for the faint of heart.
Yeah.
And in actuality, I'm not sure if all people that are writing applications actually need to use Vulkan. It will be more common that they interface to engines. So the engine developers are the ones that really need to take advantage of the features of Vulkan. But the application developers may end up writing their applications more by interfacing to the engine. But it's not for the faint of heart. That is true.
You mentioned that besides graphics, the compute AP or the compute part of Vulkan is getting, or compute is getting more important. Do you expect, and this is also shown on the SPIR-V level, right? I mean, there's still the distinction between graphics and compute on that level. Do you expect major changes along those lines? And what are the big challenges there?
I think I'm going to let Tom answer that one.
I would say come to the Kronos Vulkan buff on Wednesday next week, but you don't need to. The answer's pretty simple. The way Vulkan operates now, a lot of my talk next week will be about how we're trying to professionalize the planning of Vulkan into the future, because we used to just kind of do stuff. Now we're trying to plan. And one of the themes that is on the table is, we call it unifying compute. And the idea is to go back to SPIR-V and reorganize the tree. If people don't know, Vulkan SPIR-V capabilities are a tree. And the top decision node is this a shader or is it a kernel? We want to reshuffle the tree so that CL and Vulkan SPIR-V is the same as far down as it can be. So that's the direction we're headed. How long it's going to take, don't know. Encouragement is always good, and your input is always good.
And I asked Tom to answer that because I wasn't sure how much I could say. Any other questions?
We're all tired. So
Yeah, it's been a long day.
let's thank Karen again. Thank you.
Yeah, thank you. Thank you.